that the reaction given here, two nitrogen dioxide gas molecules react to form one dinitrogen tetroxide molecule. And the reaction has an equilibrium constant Kc equal to 0.11 at 300 Kelvin. The question asks, what is the value of the equilibrium constant for, and I'll just cut to the chase here, when the reaction is flipped, and flipped means the reactants and products have been flipped. Now, before I solve this problem, I do want to go over a few basic things about equilibrium constants that were covered in the lecture outline, but I think it's useful to think about them as we go. So first off, for a reaction, and we'll start with this reaction right here, two nitrogen dioxide gases, and here is my version of an equilibrium arrow up here that I can put in homework assignments pretty easily. And here is how I typically draw it when I write it by hand. These two, they're both double arrows. They're what I call equilibrium arrows. Or equilibrium arrows, since there's two of them. And again, any time you see an arrow that has two heads, I think sometimes I even draw it as a less than sign, a dash, and a greater than sign. Let me get that on camera. So that's a double arrow as well. Now let me write my product here. I don't need my one, but again, I tend to write it in when I make these questions for reasons that help me to put these into the computer. What this double arrow says is that the reaction can go in the forward direction to turn 2 moles of nitrogen dioxide into 1 mole of dinitrogen tetroxide, and that at various times this reaction can go in the reverse direction, and that there is an equilibrium between these two, meaning that when we reach equilibrium, two things will happen. One is, what's equal about equilibrium is that the amount of reactants and products will stop changing, and why we call it dynamic equilibrium is at equilibrium the forward and reverse reactions are occurring at the same rates. And we just did a whole chapter on rates, and so it seems like this is one of the next logical steps. That's why this chapter comes after the kinetics chapter. At equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. And what we're really tackling here is that this thing called the equilibrium constant, and there are two different equilibrium constants, and we'll do both of them before we solve this problem. There's K sub C. This is a capital K and a lowercase c, and the equilibrium constant, what I call the equilibrium constant expression, is equal to products in the numerator raised to coefficients, where the coefficient here is a 1, and I don't have to write it. I can. And then divided by reactants raised to the power of coefficients. So that is what I would call the equilibrium constant expression for this reaction. And we're given a value for it, and it's equal to 0.11 at 300 Kelvin. And a couple notes here. One is that you will have to be given equilibrium constant numbers or values. We don't know how to get them just yet. And that the equilibrium constant is a function of temperature. So whether I tell you or not, each of these equilibrium constants is at a specific temperature. And we can also write what's called a Kp if there are gases only in the reaction. And a Kp expression is partial pressures of products. So P N2O4, here's my product. This is the partial pressure of dinitrogen tetroxide raised to the first power over the partial pressure of nitrogen dioxide, so P sub NO2, and that is squared. So this is both a Kc and a Kp expression for this. And we don't know the Kp value. One of the later problems tackles the relationship between Kc and Kp. There is one. Any questions so far? If not, then let's keep going. And actually solve this problem. This one says, what is the value of the equilibrium constant for the reverse reaction, meaning that I've flipped the reactants and products. And so I'm going to call this, I'm going to just do this in a different color. So I'll write out the reaction. And I'll write out the Kc expression. So Kc for this reaction is going to be products squared. That's always how you write equilibrium constant expressions. It's always whatever the products are raised to the coefficients divided by whatever the reactants are, raised to the coefficients where I don't have to write my 1. And sometimes what we do is we might call this Kc1 just to differentiate it from the other Kc, since there's a lot of Kc's flying around here. And what I'm going to suggest is that Kc1 with NO2 squared in the numerator is actually 1 over Kc. So I'm going to write equals 1 over the Kc that's up here. And that is a true statement always, meaning that if you flip reactants and products, you take and 1 over the equilibrium constant. So, since we know that Kc for this top reaction is 0.11, we put 1 over 0.11. We type it into our calculator. 0.11, I hit the 1 over x button, and I get 9.09 or 9.1. Typically, I always enter it in 3 sig figs, so 9.09 is fine. You'll also see that since there's only 2 sig figs in this answer, 9.1 is fine as well. So the answer here would be 9.1. Any questions about that?